Welcome to this walkthrough of LeetCode problem number 1676, lowest common ancestor of a binary tree 4. In this problem, we'll dive into the task of finding the lowest common ancestor of a given set of nodes in a binary tree. This is a fascinating challenge that combines tree traversal techniques with algorithmic problem solving. Let's get started. In this problem, you are given the root of a binary tree and an array of nodes, called nodes, where each element in the array is a reference to a node within the tree. Your task is to determine the lowest common ancestor, or LCA, of all the nodes in the nodes array. The LCA is defined as the deepest node in the tree that has all the nodes in the nodes array as its descendants. It's important to note that a node can be considered a descendant of itself. The input consists of the root of the binary tree and the array nodes, and the output is a reference to the LCA node. For example, if the input root represents the binary tree 3516208 null null 74 and nodes is, for a 7, the output would be 2 because node 2 is the lowest node that has both 4 and 7 as descendants. To better understand the problem, let's look at the structure of the binary tree for the input example. The tree is visualized as having root 3 with children 5 and 1. Node 5 has children 6 and 2, and node 2 further has children 7 and 4. Node 1 has children 0 and 8. In this example, the nodes array contains 4, 7. If you examine the tree, you can see that both 4 and 7 are located in the subtree rooted at node 2. Hence, the lowest common ancestor of 4 and 7 is node 2. Another example is when the nodes array contains only one node, such as 5. Since a node is always a descendant of itself, the LCA in this case is simply 5. Now let's consider a third example. The binary tree structure remains the same, but the nodes array is 6, 4. If you look at the tree, both nodes 6 and 4 are located in the subtree rooted at node 5. This makes node 5 the lowest common ancestor of 6 and 4. As a reminder, the constraints of this problem include unique node values and a tree size that can go up to 10,000 nodes. This means your solution must be efficient enough to handle large trees while adhering to the rules of binary tree structures. Additionally, there are a few edge cases to keep in mind. First, if the tree contains only one node and the nodes array contains that node, the LCA is simply the node itself. Second, if the nodes array contains multiple references to the same node, the result is still the node itself because it is its own ancestor. Third, if nodes contains the root node along with other nodes, then the root will be the LCA if it is the common ancestor of all nodes in the nodes array. Finally, for trees with large depth, your algorithm must efficiently identify the LCA even when the tree approaches its maximum size of 10,000 nodes. These scenarios highlight the importance of designing an optimized solution that handles both typical and edge cases effectively. To solve problem number 1676, the goal is to determine the lowest common ancestor, or LCA, for a set of nodes in an arbitrary binary tree. We explored multiple approaches, each with its own advantages and limitations. The first is the brute force approach. This involves finding the path from the root to each node in the given list of nodes, then comparing these paths to locate the deepest common node. Essentially, for each node in the list, we perform a depth-first search to build its path from the root. The LCA is determined by comparing these paths and stopping at the last shared node. While this method is conceptually simple, its complexity is proportional to the number of nodes in the tree times the height of the tree, or O(n*h). This is because we repeatedly traverse the tree for each node in the list. However, its inefficiency becomes more pronounced as the number of nodes in the list increases, requiring multiple traversals. The second approach is the recursive single-pass method, which is both more elegant and efficient. Here, we adapt the classic recursive LCA algorithm to handle multiple nodes instead of just two. Starting at the root, the recursion checks whether the current node is part of the target nodes. If it is, the node is returned. Otherwise, we make recursive calls to the left and right subtrees. If both subtrees return non-null values, the current node is identified as the LCA. If only one side returns non-null, that result is propagated upward through the recursion. This recursive single-pass approach has a time complexity of O(n), where n is the number of nodes in the tree, as it only visits each node once. It's a highly efficient and elegant solution, naturally handling cases with multiple nodes in just a single traversal. Another method we considered is the iterative parent tracking approach. In this method, we perform a depth-first search to build a parent map, which tracks the parent of each node. Once this parent map is constructed, we identify the LCA by iteratively traversing the parent pointers of the nodes in the list and finding their intersection. While this approach is also efficient, with a time complexity of O(n) for building the parent map, it requires additional memory for storing the parent relationships. Furthermore, its implementation is more complex compared to the recursive approach. Considering these options, we selected the recursive single-pass method as our strategy. The key insight here is that the LCA of the given nodes is the first node encountered during a bottom-up traversal that contains all the nodes as descendants, whether directly or indirectly. This allows us to extend the classic LCA algorithm in a way that is both efficient and intuitive. The recursive single-pass approach was chosen for several reasons. First, it is highly efficient, as it traverses the tree in just one pass, achieving an optimal time complexity of O(n). Second, it is simple to implement. The recursive structure avoids the need for additional data structures like parent maps, which can introduce overhead. Third, it is scalable, handling larger inputs gracefully without requiring repeated traversals or excessive memory usage. When comparing this approach to the alternatives, the brute force method, while straightforward, becomes impractical for larger trees or longer node lists due to its repeated traversals and higher complexity. On the other hand, the iterative parent tracking approach is efficient but adds implementation complexity and requires extra memory to store the parent relationships. The chosen recursive method strikes the best balance between efficiency, simplicity, and scalability. By leveraging the inherent properties of binary trees, it provides an optimal solution to the problem, making it both clean and effective for finding the lowest common ancestor of multiple nodes. The problem asks us to determine the lowest common ancestor, or LCA, of a given set of nodes in a binary tree. The LCA is defined as the deepest node in the tree that is an ancestor of all the nodes in the set. To achieve this, we extend the classic approach for finding the LCA of two nodes and adapt it for multiple nodes. The algorithm begins by defining a recursive function, findLCA, which takes the root of the tree and a set of nodes for which to find the LCA. Using a set for the input nodes is crucial because it allows for constant time lookups to determine if a node is part of the input. The base case for the recursion handles situations where the current node is either null or one of the nodes in the input set. If the node is null, there's no further processing needed, and we return null. If the node is part of the input set, we return the node itself, as it is a potential LCA. The recursive part of the algorithm then delves into both the left and right subtrees to search for nodes in the input set. Once we've made recursive calls to both the left and right subtrees, we combine the results to determine the LCA. If both the left and right results are non-null, it indicates that nodes from the input set are found in both subtrees. In this case, the current node becomes the LCA. If only one of the results is non-null, we return that result, as it represents the subtree that contains all the nodes we're looking for. If both results are null, we return null since no nodes from the input set are found in the current subtree. The recursion starts at the root of the tree and propagates upward, eventually identifying the LCA of the entire input set. Key insights into this algorithm include its reliance on recursive traversal to explore the entire tree, the use of a set for efficient lookups, and a divide-and-conquer approach that processes the left and right subtrees independently before combining their results. The algorithm is also robust against edge cases, such as empty trees, empty input sets, or scenarios where all nodes in the set point to the same single tree node. Handling edge cases is an important part of this algorithm. If the tree itself is empty, the result is null since there are no nodes to process. Similarly, if the input node set is empty, we also return null because there's no LCA to find. Additionally, if all the nodes in the input set correspond to the same single node in the tree, that node is trivially the LCA. The implementation relies on a binary tree structure where each node contains attributes for its value, left child and right child. We also use a set to store the input nodes for efficient lookups during recursion. In terms of complexity, the time complexity of the algorithm is O(n), where n is the total number of nodes in the tree, as each node is visited exactly once. The space complexity is O(h), where h is the height of the tree, due to the recursion stack. Optimizations include the use of a set for fast input lookups and stopping recursion early when both left and right subtrees yield valid results, as further exploration is unnecessary. To better understand the algorithm, we can walk through a concrete example. Consider the binary tree visualized here, where the root node has a value of 3, and we are tasked with finding the LCA of the nodes with values 6, 4, and 7. We start at the root node, 3, and recursively explore its left and right subtrees. In the left subtree, rooted at 5, we continue the recursion. The left child of node 5 is 6, which is part of the input set, so we return it as a result. The right child of node 5 is 2, where we further explore its left and right children. The left child, 7, is also in the input set, so we return it. Similarly, the right child, 4, is found in the input set, so we return it as well. At node 2, both left and right results are non-null, indicating that node 2 is the LCA for nodes 7 and 4. Combining results at node 5, we find that the left subtree gives us node 6, while the right subtree yields node 2. Since both are non-null, node 5 becomes the LCA for all 3 nodes. In the right subtree of the root, node 1 provides no matches, so it returns null. Finally, at the root node 3, the left result is 5, and the right result is null, confirming that the overall LCA is node 5. The output is therefore 5. This code solves the problem of finding the lowest common ancestor, LCA, of a set of nodes in a binary tree. The lowest common ancestor function takes the root of the tree and a list of nodes as input. The first step is to convert the list of nodes into a set for efficient lookup, as we will frequently check if a node is part of the target set. The recursive helper function performs the main computation. It starts by checking if the current node is null. If so, it returns none, indicating that this path does not contain any of the target nodes. If the current node is in the target set, it is immediately returned as it could potentially be the LCA. The function then recursively explores the left and right subtrees to determine if the target nodes are found in those branches. If both left and right recursive calls return non-null values, it means the current node is the lowest common ancestor, as the target nodes are split between the left and right subtrees. If only one of the left or right recursive calls returns a non-null value, it means the target nodes are all located in one subtree, so the result from that subtree is propagated upward. Finally, the helper function is invoked with the root node, and the result is returned as the LCA of the given set of nodes. This implementation efficiently finds the LCA by leveraging the properties of binary trees and recursion, ensuring correctness and clarity. Here, we begin implementing the solution to find the lowest common ancestor of multiple nodes in a binary tree. First, we define the tree node class, which represents each node in the binary tree. Each tree node has a value, along with left and right child pointers, both initialized to null. Then, in the solution class, we define the method lowest common ancestor. This method takes the root of the binary tree and a list of target nodes as input. To optimize the lookup of target nodes, we convert the list into a hash set, which allows for constant time membership checks. After this, we call a helper function, findLCA, to recursively determine the lowest common ancestor. The helper function is designed to traverse the tree and identify the ancestor shared by the given nodes. The helper function findLCA begins by checking if the current node is null. If it is, we return null, as there is no further tree to explore. Next, we check if the current node is one of the target nodes by seeing if it exists in the hash set. If it does, we return the current node as it's part of the desired result. Then, we recursively call findLCA on the left and right subtrees to continue the search. If both left and right recursive calls return non-null nodes, it means the current node is the lowest common ancestor, as the target nodes are found in separate subtrees. In this case, we return the current node. Otherwise, we simply return whichever child is non-null, as that indicates the subtree containing the target nodes. This recursive logic ensures that the function efficiently identifies the lowest common ancestor in the binary tree. To solve the problem of finding the lowest common ancestor, let's begin with the first example. The given binary tree has a root node 3, with child nodes 5 and 1, and further descendants is shown in the structure. The input specifies the nodes 5 and 1, and our goal is to determine their lowest common ancestor. First, we start at the root node 3 and convert the input list of nodes into a set, node_set equals 5, 1 for quick lookup. We then call the helper function on the root node 3. Since 3 is not part of our node_set, we recursively explore its left and right children. When we move to the left child, node 5, we find that it exists in the node_set, so we return it as a potential LCA candidate. Similarly, when we check the right child, node 1, we also find it in the node_set and return it. Back at the root node 3, since both the left and right subtrees have returned non-null values, 3 is determined to be the lowest common ancestor. Thus, the output for this example is 3. Now let's look at the second example, where the tree structure is slightly different. The root node is still 3, but this time the input nodes are 6 and 2. Again, we start at the root node 3 and create a set from the input nodes, node_set equals 6, 2. Since 3 is not in the set, we proceed to explore its children. First, we move to the left child, node 5. Node 5 itself is not in the set, so we continue searching deeper into its left and right subtrees. When we reach the left child of 5, node 6, we find it in the node_set and return it. Next, we explore the right child of node 5, which is node 2. Since node 2 is also in the node_set, we return it as well. Now, back at node 5, both the left and right subtrees have returned non-null values, specifically 6 and 2. This means that node 5 is the lowest common ancestor of 6 and 2. We then check the right child of the root node 3, which is node 1. Since node 1 is not in the node_set and has no children, it returns none. This concludes the processing for the subtrees of node 3. At this point, we are back at the root node 3. The left subtree has returned a non-null value, which is node 5, while the right subtree has returned none. Since only one subtree contains valid results, we propagate node 5 upwards as the final answer. Therefore, the output for this example is 5. Moving on to the third example, we have a much simpler binary tree with just two nodes, root node 1 and its left child, node 2. The input specifies only node 2. Starting at the root, we again convert the input into a set, node_set equals 2. Since the root node 1 is not in the set, we explore its left child, node 2. Here, we find that node 2 is present in the node_set, so we return it. Back at node 1, since it has only one non-null child, we propagate the result upwards. The lowest common ancestor in this case is node 2, so the output is 2. Let's examine the time complexity of the solution for finding the lowest common ancestor of a binary tree for. The overall time complexity is O(n), where n represents the number of nodes in the binary tree. Here's how that breaks down. First, converting the input list of nodes into a set takes k time, where k is the number of nodes in the nodes list. This step involves iterating through the list and inserting each element into the set, which is a linear time operation. Since k is typically less than or equal to n, this step contributes at most O(n). Next, the recursive traversal of the tree, which is a depth-first search, visits each node exactly once. For every node visited, the algorithm performs a constant time set lookup to check if the node exists in the set. As a result, the traversal dominates the overall time complexity, making it O(n). Now, let's analyze the time complexity for the best, average, and worst-case scenarios. In the best case, if the root itself is the lowest common ancestor, for example, when the nodes list contains only the root, the algorithm still traverses the entire tree, resulting in O(n). For the average case, in balanced trees, the recursion explores both subtrees partially, but since all nodes are eventually visited, the time complexity remains O(n). In the worst case, such as a skewed tree resembling a linked list, the recursion still visits every node, leading to O(n). Moving to space complexity, the solution requires h plus k space, where h is the height of the binary tree, and k is the size of the nodes list. The memory usage comes from two main sources, the recursive call stack and the set storage. The call stack uses space proportional to the tree's height. For balanced trees, the height is O log n, while for skewed trees, it's O(n). The set storage adds an additional O(k), as it stores the k nodes from the input list. This leads to a total space complexity of h plus k. For the best case, in a completely balanced tree, the height is O log n, so the space complexity becomes O log n plus k. In the average case, the space complexity remains O, h plus k, as the tree height varies based on its structure. For the worst case, in a skewed tree, the height is O, n, resulting in O, n plus k, space usage. Now, let's compare this solution with a naive approach. A brute force method might involve finding all ancestors for each node in the nodes list and comparing them to identify the lowest common ancestor. This would require O, k asterisk h, time, where h is the height of the tree, as finding ancestors involves repeatedly traversing up the tree. In contrast, the provided solution is far more efficient. It computes the LCA directly in O, n, time using a single traversal of the binary tree. By processing each node only once and leveraging constant time set lookups, this algorithm optimizes both time and space efficiency. Finally, let's solidify the understanding of the provided solution's efficiency with a mathematical proof for its big O complexity. For a tree with n nodes, the algorithm visits each node exactly once during the depth-first search traversal. At each visit, it performs constant time operations, such as set lookups and comparisons. This makes the total time complexity O, n. As for space complexity, it arises from two components, the recursion stack, which depends on the tree's height, and the set used to store the nodes list. The recursion stack contributes O, h, space, where h is the tree's height, while the set storage contributes O, k. Combining these, the overall space complexity is O, h plus k. This balance of time and space efficiency highlights why the provided solution is optimal for finding the lowest common ancestor in this problem. When tackling this problem, there are a few common mistakes to watch out for. First, one of the most frequent errors is not handling the case where one or more target nodes are not in the tree. If you proceed without validating that all target nodes exist, your algorithm might return incorrect results. Always ensure that every target node is a part of the tree before running your solution. Next, it's easy to confuse the base case and recursion. For example, if you forget to check whether the current node is one of the target nodes or null, it can lead to infinite recursion or incorrect answers. A robust base case should return the node if it's part of the target set or null otherwise. Another mistake is traversing the entire tree repeatedly for each target node. This is highly inefficient and leads to redundant computations. Instead, you should use a single traversal to find the LCA for all nodes in the set. Lastly, if you're working with large trees or trees with significant depth, ignoring the recursion depth could result in a stack overflow. For very deep trees, consider using an iterative approach with a stack to avoid this issue. Another potential pitfall is incorrectly merging results from the left and right subtrees. If both subtrees return valid nodes, that means the current node must be the lowest common ancestor. Failing to handle this properly can break the logic of your solution. Now, from an interview perspective, this problem is an extension of the classic lowest common ancestor problem, but it involves multiple target nodes. Interviewers often use this question as a gateway to explore your ability to generalize algorithms to other structures, such as n-ary trees or graphs. To impress, emphasize the efficiency of a single DFS traversal and explain why stopping the recursion as soon as the LCA is found is optimal. Communication is key. Take the time to clearly articulate your base cases and recursive logic, as interviewers will be looking for clarity in how you handle edge cases. Be prepared for follow-ups on edge cases like all target nodes being on the same path, highly unbalanced or skewed trees, or situations where some target nodes are missing. These scenarios test the robustness of your solution. This problem also connects to several other related problems, which can help you understand it in a broader context. For instance, problem number 236, the lowest common ancestor of a binary tree, is the foundational problem for LCA algorithms involving just two nodes. It's a great starting point for building your intuition. Another relevant problem is number 1123, the lowest common ancestor of deepest leaves, which is a variation where you find the LCA for the deepest nodes in the tree. While problem number 167, 2sum2, might not seem directly related, it tests similar optimization skills, especially in avoiding redundant work. Finally, problem number 863, all nodes distance k in binary tree, involves tree traversal and understanding node relationships, which aligns closely with the skills needed for LCA problems. Exploring these problems can deepen your understanding of the concepts involved and help you refine your approach. There are a few alternative approaches to consider, each with its own trade-offs. The most common and optimal method is using recursive DFS. In this approach, you traverse the tree recursively and return the current node if it's in the target set. If both subtrees contain target nodes, the current node is identified as the LCA. While this method is simple and efficient for balanced trees, it can lead to stack overflow in deeply nested trees due to recursion depth. Another approach is to use parent pointers combined with a set lookup. By tracking parent pointers for each node, you can traverse upwards to find the LCA. This method avoids recursion but requires extra space and can be less elegant than DFS. Lastly, you could use an iterative DFS with a stack. This avoids recursion-related issues and can be applied to find the LCA. However, it is generally more complex to implement cleanly and requires careful handling of the stack operations. Each approach has its strengths and weaknesses, so choose the one that best fits the constraints of your problem. In conclusion, this problem demonstrates the importance of recursion and tree traversal techniques in solving complex binary tree problems. The lowest common ancestor is a fundamental concept, and mastering it will help in tackling many similar challenges. Thanks for watching, and be sure to check out more solutions to keep improving. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!